Time to dilate. All right, and again, first page, some GeoGebra steps, which we'll talk about. But let's get into the by hand methods of dilating. And dilations are different than the translations, reflections, and rotations that we've done, in that dilations actually do change the size of a pre-image. So it's no longer an isometry or a rigid motion. We're now looking at whoop or ooh. So it's either going to blow up or shrink. So a dilation is a transformation in which a figure is enlarged or reduced with respect to a fixed point, which we're going to use the origin in this book. The center of dilation. The scale factor, there's a big word, very important word for this lesson. And the universal scale factor variable is always a K. That's the ratio of the lengths of the corresponding sides of the image and the pre-image. All right. And again, pre-image is the normal letter, and image is the prime. So we're going to roll with that. And here's your main formula, party people. The scale factor is the image over the pre-image. So K is going to equal the image over the pre-image. So where it ends up divided by where it starts. That's going to drive you home in this lesson. So let's take a look. The dilation does not change any line that passes through the center of dilation. It maps a line that does not pass through the center of dilation to a parallel line. Here's the key from the notes right here. When a scale factor is greater than 1, it's an enlargement. When it's between 0 and 1, it's a reduction. And then we're going to take a look a little bit later when it's less than 1, what happens. So you're mainly looking for proper fractions versus improper fractions when you're talking about enlargements or reductions. First example is find the scale factor. So we just talked on this page about what the scale factor is. We got image over pre-image. Let's take a look at this paper clip. The scale factor, let's see, tell whether it's a reduction or an enlargement. So in this first one, you want to look for normal P versus P prime. So normal P, the pre-image is 8, and then this dilation takes the image up to a distance of 12. So our scale factor is always image over pre-image, so 12 over 8. So now this is an improper fraction. We can take a 4 out of each one, so reduce it where necessary. And since it's an improper fraction, then we're looking at K being greater than 1. So this is an enlargement. And it's pretty logical, right? It got bigger. So there you go. When you're doing a scale factor, it can be written as a fraction, a decimal, or a percent. So if you're taking a look at decimal representation, you'd have 1.5. Percent would be 150%. This thing got blown up. So if it's greater than 1, it's going to be greater than 100%. Taking a look at the next one. We've got, let's go green on this one. So there's my pre-image P and my image P prime. And actually this one got smaller. So my scale factor, image 18, pre-image 30. So take a 6 out of each one. Oops. And you have 3/5. Aha. So there's a look at a reduction between, because K is between 0 and 1. It's a proper fraction. So the dilation, the scale factor is 3/5. And we would call this a reduction. It's getting reduced. Whoop, whoop. All right, so that's finding the scale factor. All right, now let's get into the good stuff. Coordinate rules for dilations. Super simple, guys. Last couple sections, we had some memorizing to do. This one, not so much. All you got to do is take your scale factor and multiply it by your coordinates, the piece of your coordinates. For all the dilations in this coordinate plane, the center of dilation will be the origin. So that's why this works. Whenever you're centered at the origin, so the book likes to keep it simple, So all you do is take your scale factor and multiply by everything. Multiply by the x and the y, and that tells you what happens. All right, so in the second example, I'm going to cheat here and use the type from the book. We have to graph ABC. So here's the pre-image, A, B, C, and then a scale factor of 2. So all you have to do, my friends, is multiply everything by 2. That's going to blow it up. It's an enlargement. So our new image is A prime, B prime, C prime. So 2, 1 turns into 4, 2. 4, 1 turns into 8, 2. And 4, negative 1 turns into 8, negative 2. So with respect to the origin, you can kind of see what's happened here. A was there. A prime goes twice as far away. B prime, C prime in that same direction. Right? So that's an example of an enlargement. Here's a reduction. Graph quadrilateral. Now they did it for us here. And we have a scale factor now of 1. Whoa, easy did. A scale factor now of 1/3. So we multiply everything by 1/3 or divide it by 3. And usually when they give you one like this, they'll do you a solid and make all the numbers divisible by 3 like they did here. So we're dividing everything by 3. I'll do the same thing on a quiz. If I'm going to make it 1/3, I'll make sure all your numbers are divisible by 3 so we don't have to mess with any fractions. So negative 3, 6 turns into negative 1, 2. 0, 6 turns into 0, 2. 3, 3 turns into 1, 1. Negative 3 turns into negative 1, negative 1. All right? So with respect to the origin, this gets reduced to a shape like that. All right, so there's a reduction, party people. Oh, now check this out. This is pretty cool here. In the coordinate plane, you can have scale factors that are negative numbers. Gasp. When this occurs, the figure rotates 180. How cool is that? So when k is greater than 0, dilation with a scale factor of negative k is the same as the composition of a dilation with a scale factor of k followed by a rotation of 180. So if you start out here and you have a scale factor of k, it's going to first blow it up to that scale factor, and then it's going to rotate it 180. So a negative scale factor affects you not only size, but it's going to rotate your figure as well. But again, for us, it's super simple, guys. You just multiply everything by whatever the negative k was, and you're good to go. So the fourth example here, graph the triangle. They have it here for us in blue. We've got F, G, H, rock, hell. And my scale factor is negative 1/2. So simply apply that to all the coordinates. So negative 4, negative 2 turns into 2, 1. So it's kind of cool how that works, right? I mean, it's here, and then it gets smaller, and it rotates 180. So apply that to all your coordinates. For us, it's the same effect. You're just multiplying all the coordinates by it, graph it, but you'll notice a rotation because of that negative on the k. All right, final example here in the notes today. Finding the length of an image. So we can basically use this formula, image over pre-image equals your scale factor, to determine some lengths. If you know the scale factor, you can kind of work backwards and find any element of this equation. So in this case, we're magnifying a spider. The magnifying glass shows the image of an object that is 6 times the object's actual size. So we got this spider, and through our magnifying glass, it looks like it's 1.5 centimeters. Determine the length of the image of the spider seen through the magnifying glass. All right? So let's see here. We know that the scale factor is k, so that's cool. And it tells us that the object is 6 times. So my scale factor is 6. My K equals 6. All right. Determine the length of the image of the spider seen through the magnifying glass. So the spider is 1.5. So that is your pre-image. So setting up the equation, I've got the image over the pre-image equal to the scale factor. So just to simply solve this one, my friends, we've just got to multiply both sides by 1.5. So the image will equal 9 centimeters. All right? And again, determine the length of the image of the spider seen through the magnifying glass. So whoop, it got bigger because our scale factor is greater than 1. So a 1.5 centimeter spider looks like it's 9 centimeters whenever you're looking at it through the magnifying glass. All right, pause the video here. You can try our last problem today and we'll wrap it up. All right, welcome back. An optometrist dilates the pupils of a patient's eyes to get a better look at what's happening inside there. A pupil dilates from 4.5 to 8. What is the scale factor? So again, we're using the same formula from above, but now we know the image and the pre-image. So hopefully you want a little something like this. Let's see. A pupil dilates from, so that's the pre-image, 4.5, to 8. So 8 is our image. Okay, so what we've got here is a situation. You don't want to leave decimal. Let me clean that up a little bit. It's a little bit messy. 4.5. So you definitely don't want to leave fractions with decimals. You don't want to have decimals inside of fractions, right? That's like, no, that's no good. So what we want to do is, there's a couple things you can do. If you want to keep it in fraction form, a cool little technique is just, since 4.5, how would you get rid of that fraction or that decimal? You could just double it. So if you double the top, you can double the bottom. That's legit. You could also just, in your calculator, divide 8 divided by 4.5 and get a decimal representation. But let's say on an SAT, they would probably keep it in this form right here. So just keep that in mind. If you have a 4.5, like this was, you know, a third on the bottom or something, you can multiply it by both top and bottom by 3. But typically in this book, if you're going to get examples with decimals inside of fractions, it's going to be a 0.5 that you can just double top, double bottom. That maintains the value of the fraction. So there is our scale factor for this particular dilation for the OD in the pupil's eye, in the patient's eyes. All right, so that's a wrap on dilations, party people. Peace!